warahmatullahi wabarakatuh and salam sejahtera. So in this video we cover the last part of this chapter. So this one is basically part 4 lah, which we cover subtopic 2.3. So this is the last one. Okay, define dielectric constant. For this chapter you will learn how to define, describe the effect of dielectric, calculate the capacitance, and how to use the dielectric constant as well as capacitance with dielectric. Okay, consider two parallel metallic plates of equal area A separated by a distance D, and the space between plates is vacuum or air. So they ask you to consider that this part between the two plates is actually vacuum or air. When the capacitor is charged, its plates have charges of equal magnitude but opposite signs, positive and negative. Then the difference V, the plates is produced. So because of difference in sign, so that means it has a different potential. So you have a delta V lah. Direction of electric field will be from the positive plates towards the negative plates. I think I show it like this. Okay, direction of electric field need to be from the positive terminal to the negative plates. This is your E. And then the surface area here of the plate represent the A. The distance between the two plates is actually D. I think most of the time you'll be seeing something similar like this. So if you have a plate like this, and the area is this surface, the distance would be this D, and it depends on whether this one is positive or negative. Okay, so that one is the D. Okay. Since D is much smaller than A, the electric field strength E is uniform between the plates. So this one we already learned in chapter 1 lah. If you have two metal plates, we assume that the electric field is uniform between those plates. Okay, the magnitude of electric field strength within the plates is given by the Gauss law. Oops. Okay, I think I might have to show like this. It's much easier. Okay, so the E here is actually this one, sigma over epsilon naught, where sigma is actually equals to Q over A, where sigma surface charge density on either side is a scalar quantity. So basically this is just the derivation. And then the most important thing that you'll be using is actually this. For parallel plate capacitor separated by a vacuum, you can use C equals to epsilon naught. So this one for vacuum, epsilon naught A over D. For a different dielectric materials other than vacuum, you can use C equals to epsilon A over D. Okay, we learn into details later on this one. Sometimes you will see that for air, sometimes they use the first one. Actually, air and vacuum has a different dielectric constant. This is what we call dielectric constant. Okay, I'm gonna write it down here instead. Obviously you have a different dielectric constant from the vacuum and air, but air is actually 1.0001 if I'm not mistaken. We check later on. And so that's why sometimes we just assume to use the second formula here. Actually instead here is permittivity of dielectric material, so I'm going to use that one instead. Okay, most of the time you guys will be using this formula unless it's stated that you have a different types of dielectric material. You simply use the second equation. Okay, this one just I add some of the derivation. Maybe later on when you check how to derive that one, maybe you can see how you get from there. But if you look at your learning outcome, you don't have to know how to derive, so I think you guys should be okay with that. Just now I did draw how about the two metal plates here, A, and this is your D. Same with this one, except most of the time I think you guys will be seeing the one with the upright position. Okay, example number 8. A parallel plate capacitor has a plates of area 280 cm square are separated by a distance 0.55. Okay, maybe you can try to draw roughly. Okay, let's say I have two metal plates. The area is constant, so here A is equals to 280 times 10 negative 4 meter square. So I just change to SI unit. Again, because you have a constant inside this equation, so we need to use SI unit. Distance D is 0.55 times 10 negative 3 meter. The plates are in vacuum, so we can use epsilon naught over here, epsilon naught equation. If a potential difference of 20.1 V is supplied to capacitor, determine the capacitance of the capacitor. Okay, that one is easy, straightforward. You can use the formula. This one comes from the formula number 2 just now. If you're looking back at your equation here, formula number 2, notice that we use epsilon naught, which indicates something that is in vacuum. Okay, miss out one V over there, so one U. Okay, and then epsilon naught actually permittivity of free space. They give you the values here, 8.85 times 10 negative 12. So you substitute over here, and then you multiply with A, which I already take out here, times 10 negative 4, and then divided by D, and then straight away you get the C, capacitance of the capacitor. Okay, let's add one slide so that I can draw something there. Question B, the amount of charge on each plate. So they give you V, which is equal to 20.1. So question B, V is given 20.1 volts. So you already have the C, which is equals to 4.51 times 10 negative 10. So if you want to find the Q, you can use C equals to Q over V. Okay, where Q is equals to CV 4.51 times 10 negative 10 multiply with 20.1. We should get the answer. Okay, the next question, they want you to find the electric field strength. So that one is easy as well. Maybe you can straight away look here. So this one is for question B. Okay, this is the same that I wrote over here, so you get the answer. And then if you want to find V, you can use V equals to ED or E equals to V over D. This one, I point this one out in the first chapter, where the last subtopic 1.4, where E is equals to V over D for uniform electric field. So because of that, I can rearrange V equals to E multiplied with D. Actually, the question want to find E anyway, so just find the E. Substitute the V and D, and you should get the E. Okay, the last question here, D, the surface charge density of each plate, on each plate. So this one is easy as well. This one is actually based on the definition of surface charge density. So density of a surface, we use that one. If volume is we use a different symbol. So this one is charge divided by surface area. Oh, actually it's written over here. Okay. Now just have to substitute the total charge Q. This one is the Q value that you got just now. And then substitute the area, which is from the question, which is this one. And then you should get the answer of sigma. This one rarely they ask in the exam, but you should know it anyway. Normally most of the time I think the question will revolve around question A, B and C. This one is okay, something extra for you to know. Okay, question number 9. A circular parallel plate capacitor with a radius of 1.2 cm is connected to a 6 volt battery. So my suggestion is that you always try to draw the plates, even though it's a simple thing, but it might help you to solve. So radius is given, R is equals to 1.2 times 10 negative 2 meter, connected to a 6 volt battery. V is equals to 6 volt. After the capacitor is fully charged, battery is disconnected without loss of any of the charge on the plates. If the separation between the plates is 2.5 mm and the medium between plates is air. Okay, so the separation is D. D here is equals to 2.5 times 10 negative 3. And in between here is air. So you can use epsilon naught straight away. Sometimes you can multiply with epsilon as well, but that one is 1.001, so it doesn't make much difference. Calculate the amount of charge on each plate. Okay, so if the separation, that one is next question. So question A, you can solve that one first. If you want to calculate the charge on each, calculate the amount of charge on each plate, you can calculate using Q. But to find Q, you have to have A first. Okay, I think I'm not sure if I want to write it again. Okay, the best way to solve this one is that you can find C first. So how to solve question number A? Step number 1, you can find the C first, capacitance of the capacitor for this one. And then the second step, once you get the C, you can relate with the potential that they give you, which is 6 volt, and you can use the equation of C equals to Q over V. So I think most of the time the question will be something like this. They actually doesn't ask you to calculate capacitance directly, but to solve, if they give you all the dimension, you have to find the capacitance first. So to differentiate between this subtopic with the previous subtopic 2.1 and 2.2 is that normally the question will give you dimension of the capacitor, like the size, the spacing, and then straight away you know that one is from the chapter 2.3. And most of the time you might be using this formula, C equals to epsilon naught A over D. I already have the D, this given 2.5 times 10 negative 3 meter. A I can find using the radius, pi r square, and I just substitute 8.85 times 10 negative 12 inside the epsilon naught. Okay, so over here in this solution, actually they do it straight 2 step in one. Maybe I can show you how to calculate separately. So if I want to calculate C first, it would be 8.85 times 10 negative 12 multiply with the A, which is pi r square, pi 1.2 times 10 negative 2 square, divided by the distance atau separation between those plates, which is 2.5 times 10 negative 3. Press your calculator, get the answer first, and then once you get that, calculate using C equals to Q over V, where Q equals to CV. Okay, you found C, substitute inside here. Okay, and V here is actually 6 from the question. Okay, the next question. If the separation is increased to 8 mm after the battery is discontinued. So you assume initially you have a battery over here. It's connected to a battery. So when it's connected to a battery, it's a fully charged capacitor. And then when it's being disconnected, the charge remains the same. Initially, let's say the 10 coulomb, then you move out, you take out the battery, you still have 10 coulomb over there. So in this case, not 10, but instead you have Q equals to 9.6 times 10 to the power of negative 12. So the Q would be constant. It will remain unchanged. So the first question, you want to find the amount of charge on each plate. So Q constant. So it will be the same with the previous one. So Q equals to 9.6 times 10 negative 12. You calculated in A. And then the difference here would be the charges. Sorry, the potential difference would be different. The V would be different. So how to calculate the V? Okay, now you have Q. You want to relate Q with V. Okay, to relate that, you might have to use a little bit of formula. If you guys still remember, the formula for electric field the formula for uniform electric field is E equals to V over D here. This one, the same with this one. Okay, and the V, if I relate with C equals to Q over V, I wrote here on the right hand side there, and then I substitute the V inside here, I will get Q over C D. And then the C from this chapter is basically equals to epsilon naught A over D. Substitute C over there. Cancel out the D, I'm left with Q over epsilon naught A, okay, which is this one. And then since I have both V over D equals to Q over epsilon naught A, I can equate those two, like what they did over here. Okay, once I have that one, I just have to substitute all the value. Q is constant, same with the pi A. Epsilon naught is 8.85 times 10 negative 12. It still remains the same because that one is still air, doesn't put any dielectric material. The A remains the same because the dimension doesn't change. This one is same, constant. And the only difference here would be D. So this one is the new, this separation. You can calculate and you should get V equals to 19.2 volt. So you can see that actually the voltage, the potential difference increased from 6 to 19.2 volt. Okay, now you want to find the new capacitance. So you can calculate using two methods. You can use C equals to epsilon naught A over D, or you can use this one, where you can relate with Q over V. So it's written over here, Okay, this one is exercise. You can try to do it. Okay, so the next one is about dielectric effect on a parallel plate capacitor. So previously what we learned is that between two plates, like plates A and plate B here, is just air. or inside a vacuum. What if there's some certain materials in between those plates? So the material that we choose normally is a insulator lah. So it will be insulator. And the reason why we want to put a material inside here is that so that we can increase the capacitance. But how does it increase the capacitance? Okay, now we can see the explanation. Okay, initially the plates are separated by a vacuum. So initially it's just a vacuum and connected to a battery, giving the charge plate Q positive and negative Q. The battery is now removed. So when you remove the battery, the charges remains on the plates. Okay, it remains constant. The electric field between the plates is uniform and has a magnitude of E naught. So we just put this one as E naught. Meanwhile, the separation between the plates is D. So this is the D, the distance D. When the dielectric material is placed in the electric field between the plates. So this is dielectric materials. The molecules of dielectric tend to become oriented. So remember that this one is not a conductor, it is an insulator. So the molecules inside there basically it wouldn't be moving around, but it will try to rearrange themselves, or we call that one become oriented. That means one polarity is to the one side and the polarity to the other side. So positive one side, negative one side, with their positive end pointing towards the negative. So you will expect, so beforehand you have a mix of oriented. This one is what we call mix oriented. Mix. Once it is under electric field, it will try to rearrange, the molecules will try to rearrange and becomes oriented. So you can see here the positive terminal here will be pointing towards the negative, while the negative will be pointing towards the positive. And the same thing happens across all the dielectric materials, all the molecules inside there. Okay, as shown in this figure. Okay, the result is building up positive charge on one surface of the dielectric and negative charge on the others as shown in figure below. So you can see that over here they built up a negative charge surface on one end, another surface is positive. For the figure before, the number of field lines within the dielectric reduced. So if you compare the complete electric field lines, you can see here is actually lesser compared to this one. This one you have a complete lots of electric field lines, but once it becomes oriented, once you put the dielectric materials, you have retarded electric field over here, over here, over here. So it means that the electric field now decreasing, just based on the diagram itself. It's partially cancel or reduce. Electric field strength is less than the initial electric field strength. Okay, and because of that, if you guys still remember where E equals to V over D, when E is decreasing, V will be decreasing as well, because D remain the same. Now one more thing that you need to remember is that the charge remains the same. Once you pull out the potential difference, you will have a constant Q. It remains unchanged. Since the V is changing, which is decreasing, you will have increase in capacitance. So this is why when you are putting a dielectric material in between two plates in capacitor, you have increase in capacitance. This is the story, but most of the time you will be doing the calculation instead. Okay, you'll still be using equation C equals to epsilon A over D. The only difference here, if initially, if you don't have any dielectric materials, we'll be using C equals to epsilon naught A over D. But now you'll be using epsilon A over D. So notice that one is epsilon naught, another one is epsilon. Epsilon is actually equals to epsilon naught epsilon R. You just have to multiply with the epsilon R. So epsilon R is actually dielectric constant. It defined as a ratio between the capacitance of a given capacitor with space between plates filled with dielectric and the capacitance with the same capacitor with plates in vacuum C0. So basically, you have the same capacitor with the same dimension like area and spacing, but the only difference here is that you have initial capacitance and final capacitance due to dielectric material. So one in vacuum, this one is in vacuum, this one is with the dielectric material. Okay, this one just rearranging and things. Okay, and then you can get the equation for V as well. And then E, you're gonna conclude. This one you can see yourself, dia punya derived version. But the important parts here, even though it's written a little bit small down here, but it's this one. So remember, from the definition, epsilon R, dielectric constant is actually a ratio of C over C0. So this is the first part. This is from the definition. Okay, if you derive a little bit more, you will get epsilon over epsilon naught, V naught over V, and E naught over E. So for V and E, the one with the vacuum will be up there. Denominator is the one with the dielectric. For C and epsilon, denominator is the one with the vacuum. Okay, so this is the dielectric constant. This is what I told you. The air is 1.001 ataupun 1.00059. So the effect is very small. That's why normally when we try to calculate in air, normally we can use epsilon naught straight away, because you basically multiply by 1. So all this epsilon R is given in the exam. They will give you in the exam, or maybe they ask you to find the epsilon R. But it's a constant. It depends on the material. The higher it is, this is actually a better. It's a better dielectric material. Okay. So example, a vacuum parallel plate capacitor has a plate of area and separation of D. The capacitor is charged, potential difference V0. Then the battery is disconnected and dielectric sheet of the same area is placed between the plates, as shown in figure below. In the presence of the dielectric, the potential difference across the plates is reduced to 500. Okay, maybe we can try to redraw the situation. So the dimension remains unchanged. The A is constant. A here is same with this A. It's basically 150 times 10 negative 4 meter square. The separation D remains the same. D, which is equals to 2 times 10 negative 3 meter. The capacitor is charged to potential difference V0, 2000 volts. So this one is for the first one. I put this one as V0. And then the battery is disconnected. The constant between the first and the second one is actually the charge. Q0 is the same for left and right hand side. And then for a new one, it says here that the potential difference across the plate is reduced to 500. So V now becomes 500 volt with the presence of dielectric materials. It doesn't state what is the value for dielectric materials, so maybe you have to find that one. Okay, let's read the question. So this is basically the ideas of the situation. Q remain constant because they basically pull out the battery. Okay, A, the initial capacitance of the capacitor. You have A, you have D. If that one's in vacuum or air, you can calculate. So air is 1.00, so you can use straight away C equals to epsilon naught A over D. So we put that one as C naught as well, because we want to differentiate between C and C naught. So C, once you have the dielectric materials, C naught is the initial before you have any dielectric materials. So in between those is just air. Okay, the charge on each plate before the dielectric is inserted. So the first one you can calculate, you use epsilon naught 8.85 times 10 negative 12. A, you can substitute 150 times 10 negative 4. D, 2 times 10 negative 3. Once you get those values, you get C naught, you can calculate the charge on each plate using C equals to Q over V. If you are talking about Q naught, you have to use V naught and C naught. So V naught is given 2000, C naught the one that we calculated just now, the Q naught which is doesn't change for first and second part, we can find straight away. Okay, I love to repeat that this one is a constant. Constant. Let's bring this one up there. And then question C, they want to find the capacitance after the dielectric is in place. So they wanted to find the new capacitance, but they didn't give you any values for epsilon, the new epsilon R. So if they give you epsilon R, then you can straight away calculate epsilon equals to epsilon naught epsilon R, and then you can calculate using this formula. But they didn't give you any values on the dielectric constant, so instead you have to relate with the V there. Q remain unchanged, so the new C is equals to Q new over V new, yang barulah. But here the charge remain unchanged, so I can put this one as Q naught, which is equal to the values before that we calculate, and then you just divide it by 500 and you should get the new C. Okay, the next question, they want you to find the relative permittivity, which is basically epsilon R. From the definition, this one is actually equals to C over C naught. I have to double check, but I think this one is correct. Yeah, it's C over C naught. I always got confused between which one is up and which one is down. C and epsilon, yang not tu kat bawah, V and E not tu kat atas. Okay, the permittivity of dielectric materials, so it just epsilon equals to epsilon R epsilon naught, the initial electric field. So epsilon R2 actually is a ratio, epsilon is the permittivity itself. So F, they want to find the initial electric field. This one is easy. E equals to V over D. We are talking about initial, I can use V naught. D is given. The electric field after the dielectric field dielectric is inserted, you can use E equals to V over D. And I think there's another method, but maybe I have to rethink about it. But I think this one is the easiest way. Okay, so this is the idea how you want to solve. Let's look at the solution. Okay, A, I thought here you need to use epsilon naught, C naught equals to epsilon naught A over D. So we can use here, substitute all the values, we should get the answer straight away. Remember to use SI unit only, because we are talking about a constant over here, epsilon naught. So once you have epsilon naught or any constant, the formula you have to use SI unit. Okay, the charge on each plate, you can use C equals to Q over V. If you arrange that one, Q equals to CV naught, and then you should get 1.3 times 10 negative 7. Question C, the capacitance after the dielectric plate this in place, you can use C equals to Q naught over V. Okay, this one, and then you can find the C. This one is the new capacitance. After that, they want to find epsilon R, which is actually, the question actually wanted to find the relative permittivity. So permittivity is epsilon, relative permittivity, you have epsilon R. It's a ratio, C over C naught. You get this one. Since it's a ratio, it doesn't have any unit. Remember? And then the E, they ask you to find the permittivity of dielectric material You already have epsilon r. You know epsilon naught is a constant, 8.85. You just multiply those two values, we should get 3.55 times 10 negative 11. F. Okay, you can use V naught over D. Ini senang, tak ada masalah. Then G, you can use V over D. Again, remain the same. Or this one is the one that I told you. Alternatively, you can use epsilon r equals to E naught over E. You already have E. Sorry, you already have E naught, you can calculate the E. If you have epsilon r, which is 4.01. Okay, so you should get all the answer for this example. Okay, for example 11, given that a parallel plate capacitor has the space between the plates filled with two slabs of dielectric constant epsilon 1 and epsilon 2 as shown in figure below. So this one is basically the epsilon r. Each slab has a thickness of d over 2, where d is the plate separation. Show that the capacitance of the capacitor is C equals to, okay, so they already give you the final form. They just want you to figure out how do you get to this C equals to so on, this one. Okay, if you have a parallel plates that sit next to each other like this, like a sandwich on top of each other, you can treat this one as a dielectric materials that is arranged in series. Because of that, the parallel plate capacitor can be considered as two parallel plate which is in series as well. I'm going to put it over there. So if you have a capacitor in series, like exactly like this diagram, you can treat that one. If you want to calculate C effective, you can use 1 over C equals to 1 over C1 plus 1 over C2. That one is the total capacitance, because the question wants you to find the capacitance of the capacitor, the total of the two dielectric materials. So you can use 1 over C1 and 1 over C2, where each C is equals to epsilon naught epsilon r A over D. Then it depends on whether this one is epsilon 1 or epsilon 2. You can substitute here. And then the D is actually D over 2, because it is given in the question, in the diagram here, D over 2. And then if you want to solve it, you just have to substitute inside the equation. You get this one, epsilon 1 epsilon naught A over, okay, and then this one as well. So I'm not going to read that one. Next, you can try to rearrange, because this one is over something. Basically this one is 1 over epsilon 1 epsilon 2 A. You can multiply that one, but you multiply with D. Okay, it is actually multiplied 2 times, so it becomes 2 over D over 2. D over 2, because it's 1 over. Or if you want to do it one by one, okay, maybe you can do it one by one. Okay, first, because this one is D over 2 is over here, okay, I can bring this one here. If I multiply it, but in opposite, I have to flip, and then I can multiply, and then this one is plus the behind term. And then because of this one is still 1 over something. I can flip that one again, and it becomes epsilon 1 epsilon naught A multiplied by 2 D will be up here. Again, the same applied for the second term. So I'm going to show you just one term, so it's basically the same. Now you end up with this one, 1 over C equals to D over 2 epsilon 1 epsilon naught. Okay, the next step, you have 2 and epsilon naught, which is the common term. I can factor that one, so I left with D over epsilon 1A, like this. I can factor out all of these, even the D I can factor out as well. So you left with that one. so maybe it's too much of a jump. I'm gonna write it over here. Factor the D, the 2, and epsilon naught, and A as well. So you left with 1 over epsilon 1 plus 1 over epsilon 2. So this is what it is. And then you just have to cross multiply. Bring this one up here, bring this one up here, and then this one becomes together. Or actually, if you guys remember, you have to multiply up and bottom with the same term lah. So if you want to add the two term, you need to have common denominator. So you multiply this one, let's say I put this one as red color, with epsilon 2. If you multiply down here, you have to multiply up here. If you multiply up here, you have to multiply down here. So now you end up with D over 2 epsilon naught A, okay, epsilon 1 plus epsilon, okay, so this is 2. Excuse my writing there. So this one will be epsilon 2 plus epsilon 1. Then I have epsilon 1, epsilon 2, epsilon 2, epsilon 1. So now I have a common denominator. I can add straight away epsilon 2 plus epsilon 1 like this. Down here you get, over here. And then I just have to flip it because this one 1 over C. Just put it 1 over something, or to the minus 1. So if I inverse that one, I get this one flip lah. Everything also flip. So I end up like that, exactly like the question gives. So here you can show that this is what happened. When you have two dielectric materials sitting on top of each other, you can treat that one as a series. So if you want to solve, you can use C equals to 1 over C equals to 1 over C plus 1 over C. Okay, I think that's all for the tutorial. That's all for the lecture notes. The next part, obviously, I want you guys to do the tutorial. Okay, I will do the video on the tutorial itself, but I really want you guys to try it first. So that one, I'm gonna hold it a little bit longer. Okay, thank you everyone for listening.